Hello. In this video, we're going to solve the four problems related to fractions and fractions that also have exponents in them. So combining two of the things that have already been presented on the video. I should have pointed out on the last video that shows solutions, I am going through these relatively quickly on the assumption that you have already yourself arrived at an answer and that you're watching this to see if your answer matches, what the correct simplification is, and that you've already worked through the steps and that you're not using these videos to actually work through the steps for the first time. If you are doing that, I would encourage you to change that methodology and actually work on them on your own first. You will learn a lot more that way, and then just use this as a check to make sure you've done things correctly, and then correct mistakes that you have made. So that's the spirit in which these are being offered. So with that, I will proceed through the first one again, and we'll start in the same way that we started with the previous problems, where we are going to multiply the denominator by its reciprocal. So we're going to multiply by 6 squared times 7 cubed over 5 squared. And I should point out all of this stuff is multiplication and division. We don't have any addition yet. Those we'll tackle that in later problems in these videos. We have 7 to the 4th times 6 to the minus 3, 5 to the 1/2 power. Now that might look a little funny, but we'll see that we can deal with 1/2 powers just as easily as we can deal with whole numbers. Multiply that by 6 squared, 7 cubed over 5 squared. So again, we're just multiplying the original ratio by something that's equal to 1. We know that the denominator becomes 1. And now we use our rules of exponents. We see 7 to the 4th times 7 cubed. So one value that's going to be in the numerator is 7. And when we have exponents that are multiplied together, so all of this would just be multiplied, all the numerators would be multiplied, the two numbers in the denominator are going to be multiplied because we're multiplying the fraction. If we were adding, we'd have a different story. But because this is multiplication, we simply add the two exponents. So 4 plus 3 is 7. In terms of the 6, we have 6 to the negative 3 times 6 to the positive 2. And again, if we add the exponents, we'd have negative 3 plus 2 for a negative 1 exponent on the 6th. Divided by, same rule here, we've got 5 to the 1/2 times 5 squared. So this becomes 5 to the 2.5 in the denominator of the numerator. The denominator of the whole ratio is equal to 1, so we could rewrite this more simply as 7 to the 7th, 6 to the negative 1, 5 to the positive 2.5. And we saw on the video dealing with exponents that if we have an exponent to the negative 1, that we can move it to the denominator. And when we do that, we convert the negative into a positive. So we change the sign whenever we move from numerator to denominator or denominator to numerator. So then we'd have 6 to the 1st. And at this point, you might recognize 6 to the 1st is just 6 raised to the first power, which is just 6. So we wouldn't really even need to write that to the first power. We do need to write 6 to the negative 1st, because while 6 to the 1st is equal to 6, 6 to the negative 1st is 1 over 6 to the 1st. So different story when we have negative 1 as an exponent. And that would be times 5 raised to the positive 2.5 in the denominator. Or if we were typesetting this and we had to have it all run in one line, we could write this as 7 to the 7th, 6 to the negative 1, 5. And then what would we want the exponent to be here? Right, negative 2.5, because we'd be bringing the positive 2.5 up from the denominator, so we have to change the sign for it to become negative 2.5. So we can also write it this way. And then at this point, we could actually take out a calculator, calculate 7 raised to the 7th. That's going to be some number. This is another number. That's another number. And we could multiply those three numbers together and get a final numeric value. I'm not interested in the final numeric value as much as I am in the manipulation of the exponents and the fractions. So hopefully you ended up with at least this. That's perfectly fine. Notice these are all equal, so any way you say it, they're all equivalent. So if you wrote this, or if you wrote that, or you wrote that, all three would be correct. This is also technically correct, but a little bit more complicated than it need to be. We could write every number that we encounter. Grocery store, why don't you give me a dozen eggs? How many eggs do you want? 12 over 1 eggs, please. You wouldn't say that. So whenever we have the opportunity to represent things more simply. Next one down. Same process. Multiply the denominator by its reciprocal. That should be x to the negative 6. We'd have 9 to the 4th times 18 to the negative 0.19. A little unusual, but what I hope to illustrate by doing that is just because something looks a little strange, we might be more familiar with squared and cubed and raised to the 4th and raised to the negative 2. But just because we have a negative decimal place there doesn't change the rules at all. So what we've done before, we can still do. So a lot of this is just pattern recognition, quite frankly. A lot of math, a lot of chemistry is pattern recognition, and I hope to talk about that in future videos. So establishing what we know based on things that are familiar and then extrapolating to what we don't know, but being confident in those extrapolations because of what we do know. Denominator, everything cancels. Denominator again becomes 1. Now what happens in the numerator? We have 9 to the 4th times 9 to the negative 5th. Again, I'm saying times because all of these things are multiplied by one another. If this were an addition or subtraction sign, we'd have to change what we do. So again, the rule of adding exponents comes into play. 4 plus negative 5 becomes 9 to the negative 1. We have 18 to the negative 0.19 times 18 to the 3rd. So we would say, what is negative 0.19 plus 3? Oops, sorry, can't see that. 0.19 negative plus 3, or in other words, 3 minus 0.19. And we see that that's going to be 2.71, 2.81. So we would have 18 raised to the positive 2.81 divided by x to the negative 6 times x to the positive 0.5. So here again, we'd have 5 plus a negative 6, or negative 6 plus 0.5. Sorry, that would be a 0.5, or negative 5.5. So we have x to the negative 5.5. Again, everything is over 1, so we could simplify this by saying 9 to the negative 1, 18 to the positive 2.81 over x to the negative 5.5. And now you see here some unusual things. We don't often see negative exponents in the denominator. We don't see negative exponents in the numerator. We could rewrite this in a different way. We could say this is x to the positive 5.5, bring the exponent up so it becomes positive. We'd leave the 18 there, and then we'd bring the 9 into the denominator. We'd have 9 raised to the first, which I'm just going to write as 9. So that would be an equivalent statement as well. So if you got here, great. If you don't like negative exponents, we could do this. Makes it look a little bit cleaner and easier to understand. Or if we wanted to write this all in one line, we would write x to the 5.5, 18 to the 2.81, 9 to the negative 1. That would be another way to represent that. So this, the initial fraction here is equal to that, a little bit more simply written, or that. Next one down. At this point, I am just going to now adopt that more efficient method that I talked about in the last video, which is just recognizing that when we want to clear this, the denominator is going to clear. when we multiply by the reciprocal. So I'm just going to multiply the numerator by the reciprocal straight away and save myself one step. So I'm now solving problems faster. And here we see a to the fourth times a to the third, a to the seventh, b to the minus 3 times b squared would be b to the minus 1. And again, we have z squared times z to the fifth, so we have z to the positive 2.5 in the denominator. And if you look at this, I've tried to do something clever here. This form that has symbols A, B, and Z is identical to the first problem we solved using numbers. Only now A stands in for 7, B stands in for 6, and Z stands in for 5. We started in essentially the same place. A, everywhere that 7 was, there's an A. Everywhere that there's a B, there's a 6 up here. And everywhere that there's a Z down here, there was a 5 here. So this problem and that problem are identical in terms of the logic and the rules that we use to solve them. And like the one above it, we could also rewrite this as a to the seventh, b to the minus 1, z to the negative 2.5 if we wanted to write it all in one line. Last problem here. Here again, just like above, I'm saving myself the step of rewriting the denominator times its reciprocal and simply multiplying the numerator by the reciprocal of the denominator, because now that we've done this a dozen times, I've convinced myself anyway that when I multiply the denominator by its reciprocal, the denominator always becomes 1. So I don't need to keep doing that. But if I did that to the denominator mentally, then I have to do it to the numerator, and I'm doing it explicitly because I don't know what the numerator is going to equal when I do that. So then at this point, we follow the rules. A to the half times a to the half is a to the 0.25 times a to the 0.25 is a to the half. Here we have something interesting. B to the minus 18 plus b to the positive 18 becomes b to the 0. We'll talk about that in a second. And then the denominator, we'd have z to the half, z to the fourth. So add those two together and we get z to the 4.5. And you might recall from previous classes, what does b to the 0 equal? Anything raised to the 0 power is equal to 1. So if we say truck raised to the 0 power, that's equal to 1. It's not equal to truck, it's equal to 1. Anything raised to the 0 power is equal to 1. So b to the 0 is 1. 114 to the 0 is 1. Negative 7,432,000 to the 0 is 1. So we don't really even need to represent that. So we would just have a to the positive 1/2 over z to the 4.5. Or again, if we wanted to write this as you see a lot of textbooks doing, this would also equal a to the 0.5 times z to the negative 4.5. This would be perfectly fine as a simplification. And again, I actually advocate leaving them as fractions because I think it's just easier to do cancellations and see exponents and things like that when we have fractions rather than negative exponents. That's a personal preference. You can decide for yourself what leads you to the most success. So try lots of different problems in lots of different ways and see what works. So hopefully that's a nice review. And again, the answers to these will be posted on another document, so you can just glance at the answers. But hopefully you have worked these out prior to viewing these videos so that you've gotten yourself into the thick of it and had to think through these problems and then arrive at the correct solution. And if you haven't arrived at the correct solution, that's something too, not a problem. It just indicates that something isn't clicking. And that's an opportunity to ask questions and learn, which is great. That's what college is all about. We don't expect you to know everything. If you knew everything, you wouldn't be going to college. So that's not an expectation. The expectation for me, as I tell my students, is that you're willing to learn. That's the expectation that I hope you come to college with, that when you make mistakes, you're not content making them again, but you recognize that mistake and say, boy, I have to learn that. I have to go back and do that differently. Just like falling off a bicycle, you aren't content to say, oh, heck, I'm never going to ride a bicycle again. No, you got back up and you tried something different. And eventually, something clicked. That's the same thing with academics. Sports, too. Man, I've tried to golf a lot. Nobody on the planet is good at golfing, and yet look at how many people golf. Right? Tennis players, musicians, the way to get good at a craft is to keep making mistakes, but not make the same mistakes twice. Stop and correct it, right? And then go on to the next challenging thing. So that's what this is being offered in. That's the spirit, and I hope you find this useful. And again, I look forward to answering questions if you have them. mark.vitha@drake.edu. Just send me an email, and I'd be happy to set up a Zoom or something and just talk, say hello, and have a good rest of your day. Thanks. Bye.